So yesterday we started talking about how reactions happen at different speeds. And so we're going to keep going with that, with talking about the rates at which reactions go. So we can predict a little bit about those rates. So for a reaction where one reactant is A and one product is B, the rate of the reaction is given by this equation right here that is called a rate law. So the rate is equal to K, which K is called the rate constant, and it is specific for each reaction, and it changes numbers all the time. So for us in this class, we just need to know that you're going to put a K for the constant times A in brackets. So those brackets stand for concentration. So anytime that you see brackets, that really means concentration, which we talked about that in chapter 16 and in chapter 17. And our concentration will probably be molarities. Okay, so that would be moles divided by liters. So in total, the rate law is the rate is equal to K times the concentration of the reactant. Okay. So the value of the K, the rate constant, depends on the conditions of the reaction, and it is only determined through experiments. So we are not actually going to solve for the value of K this year because you just have to use experimental data to solve for it. And the value of the rate constant in a rate law is very large if the products form quickly, and it's very small if the products form slowly. So looking at numbers, that can help you determine that. Now, large versus small, I would say like a large number would be like times 10 to the positive like 4 or bigger. You know, like a really big number, positive exponents on the times 10 mean that it's very large numbers. And if it's small, I would say like times 10, negative exponents are decimals. So like -4, okay? So if it's larger or smaller than those, then it's definitely large or small. And then you can predict if the products are gonna form quickly or slowly based on that number. So I might have you look at a number for K, but I might not. You're not gonna solve for K. So in addition to having the rate equals K times the concentration, we also have what are called orders. The order of a reaction is the power to which the concentration of a reactant must be raised to match the experimental data. So if it's a 1, we call that first order. So in the example we just had, that kind of actually was first order because there was no exponent there. So that's implied that it's 1. In a first order reaction, the rate is directly proportional to the concentration of only one reactant. So that means that if the concentration of A is reduced by half, then the reaction rate is also reduced by 1/2. It's just, it does exactly the same thing, okay? You could also have more than one reactant, which happens a lot. So you can have more than just first order. So sometimes this is just a generic equation for double replacement where reactants A and B react to make products C and D. The lowercase symbols or the lowercase letters are the coefficients in front. And so for the reaction when you have multiple reactants, the rate law at the bottom here just tells you that you just have to take all of the concentrations of the reactants only raised to a power. Now, the X and the Y are just spot fillers. We don't know what they are, so we have to fill something in there, but you could use whatever letters you want to. Notice how I used different letters than the coefficient letters because the coefficients don't come into play. The coefficients don't tell us anything about the rate law. Okay, so now with the rate law, if both of the exponents are 1, then the reaction is said to be first order in A and first order in B. And you can actually add those together to get what's called the overall rate law, or the overall order, which you just add up all of those orders, and so 1 + 1 is 2. So it would be second order overall for that reaction. But just remember, don't assume that the coefficients are equal to the exponents, because they're not always the same. And when writing rate laws, you just want to make sure that you're including only things that are labeled as gaseous or aqueous. This is because their concentrations cannot change, so they don't have an effect on the rate of the reaction. So only aqueous and gas can be included, not solid or liquid, and only include reactants. Don't include products. So we want to write for both of these equations, the generic rate laws. So we don't know very much information, but we can still write a little bit down. So for the first reaction, the N2 plus the 3H2 makes 2NH3. They're all gases, but we don't include the products. We only include the reactants. So it would be rate is equal to K times the concentration of N2 raised to a power, I don't know what it is, so I'm just going to put X, times the concentration of H2 raised to a different power, so I put Y. So they have to be different. And that's it. Now, technically, like if you write the 3 next to the H2, that's going to be okay. You don't have to. So that's why I didn't do it. But that's all we would do for generic rate law. Okay. So now for B, we have HCl aqueous plus NaOH solid to make NaCl aqueous plus H2O liquid. So we're not going to include the solids or the liquids, and we're not going to include the products. So that means the only thing that we have to include in the rate law is the HCl. So the rate is equal to K times the concentration of HCl raised to a power of X. If you really don't like X and Y and Z and all those things, you can change it. I don't really care. Okay. That seems like a good place to stop.